After introducing the concept of phasor and analyzing steady-state circuit with frequency analysis, we've introduced two applications, resonance and mutual inductance. From this lecture on, we'll introduce a third application, three-phase circuits. The three-phase circuit is the most common form of power transmission in power system. It has higher efficiency than single-phase circuit and higher reliability than polyphase circuits, so it has a wider use. In order to study three-phase circuit, we must introduce three-phase source firstly. This is the concept of this lecture. This is a diagram of a generator's internal structure. The middle part is called the rotor, whose rotation is driven by prime motor. The surrounding part is called the stator, whose position is static. We've introduced you the photos of the rotor and the stator in lecture 60. For three-phase generator, one pair of coil is arranged on the stator every 120 degrees. This is AX coil. By coil, BY coil is 120 degrees after AX. CY coil is 100 degrees after BY. On the rotor, N represents a north pole and S represents a south pole. When the rotor is rotating driven by the prime motor, the coils on the stator cast magnetic lines of force that generate introduction electromotive force. If the coils are connected to the load, there will be current. Let's see. Pause it here. Now the north pole of the rotor points to B and the south pole points to Y. According to the knowledge of physics, we know BY coil gets a maximum electromotive force now. It can be seen from the waveform. Similarly, when the north pole cuts A phase gets the maximum electromotive force. When the north pole cuts C phase gets the maximum electromotive force. From the flash, we can find that after the three coils each differ 120 degrees among each other, are cut by the magnetic lines of force produced by rotor, their induced current differs 120 degrees among each other. Three coils have 6 terminals. Terminal A, B, and C are called the start terminals, and terminal X, Y, and Z are called the end terminals. It doesn't matter that which terminal is A, because they are symmetrical in the structure. But once we define one terminal as A, the terminal opposite to it is X. The terminal lags A 120 degrees in the rotating direction is B, and the terminal opposite to B is Y. The terminal lags B 120 degrees or leads A 120 degrees is C, and the terminal opposite to C is Z. In other words, the terminals A, B, C, X, Y, Z can be defined as you like, but once one terminal is defined, the other 5 are determined accordingly. From the flash, we can find that the three-phase generator can generate 3 single-phase voltage sources with the same frequency, same magnitude, and 120 degrees phase difference among each other. The 3 single-phase voltage sources are called the balanced or symmetrical three-phase sources. Next, let's analyze the characteristics of the 3 sources. We suppose the initial angle of UA is 0. Because B lags A 100 degrees in space, UB lags UA 100 degrees in the phase. C lags B 100 degrees in space, so UC lags UB 120 degrees in the phase. One cycle is 360 degrees, so UC leads UA 120 degrees. These are the time domain expressions. Their corresponding phasors are like this. Let's draw the phasor graph. UA, this is UA, it rotates counterclockwise with the angular frequency omega. UB lags it 120 degrees. UC lags UA 120 degrees and lags UB 120 degrees. By the phasor addition, we can find that UA plus UB equals negative UC. In other words, UA plus UB plus UC equals 0. This is concluded from the phasor graph. You can get the same conclusion by adding the time domain expression together. This means that the sum of the instantaneous voltage and the phasor voltage of the balanced three-phase source are both zero. The three single-phase sources with same frequency, same magnitude, and 120 degrees phase difference among each other have two connection types. The first type, all the terminals are connected together. It's called the star connection. In the second connection, A is connected to Z, B is connected to X, and C is connected to Y. It is called the delta connection. We need to introduce the definition of several terms about the star connection and the delta connection. The first is the terminal line or the fire line. The line connected to the star terminal is called the terminal line. For example, ABC lines in the diagram are the terminal lines. In the common high voltage AC transmission lines, such as the compact transmission line in the picture, the three lines are A, B, and C terminal lines or fire lines. Besides, if there's another line connected to the neutral point of the star connection, it's called the neutral line. So three-phase source has several different forms to the external circuit. If it contains A, B, C, N four lines, the form is called the three-phase four-line system. If it contains only ABC lines, the form is called the three-phase three-line system. The current flows through every terminal line is called the line current. They are shown in the figure. The voltage between the terminal lines is called the line voltage. They are UAB, UBC, and UCA. Besides the voltage and the current relationship between the terminal lines, we are also interested in the voltage and the current of every phase in the source and the load. So the phase current is the current flow through every source. Similarly, every phase has its phase current. Do you find the voltage and the current of every phase are in common a non-associated reference direction, whether it's star connection or delta connection? It implicitly means that the source provides power to the external. In the following lecture, when we discuss the load, the direction of the phase current and the phase voltage is associated. It implicitly means they absorb power. Well, this is the end of the lecture about three-phase sources.